Hello, everybody. So my name is Niall Douglas. Probably may have heard of me, or you may not. I've been sitting at the back here at these meetings since January or so, and I have to say it's great. C++ users meeting. It's very good. So thanks very much for that, for organizing everything. It's yeah, it's definitely above average. So it's well worth attending. Anyway, I kept myself quiet and said nothing. Hopefully, none of you noticed I was there. But anyway, no, I decided that I probably should give a talk before I left, so my contract will be up fairly shortly. So yeah, I was able to come and do this. So yeah, let's see. I don't know if I'm on the standards committee yet, because nobody knows until you are. Even if you turn up, doesn't mean you're actually a part of the member or not. I suppose the best way of knowing if you are or not is whether they loop you in to private email. And if that's the case, then yes, I must be. I have been part of Boost, though, for, technically it's something like 15 years, but nobody knew until about 2012 or so. So something like that. And I was lead admin for Google Summer of Code for many, many years. We brought in about $150,000 of funding, and we put lots of very promising students through, including the Boost HANA library. So that was really good to see. So anyway, this talk is about some of my more recent Boost and committee work. I'm going to loop in some other committee work. I apologize in advance for this mostly being a talk about committee stuff, but you might actually have something to do with C++ too. We'll wait and see. Kind of interesting. So the first thing we have is I'm going to talk a little bit about what is disappointment. Reason why is because it needs to define it. It could be anything, couldn't it? It could just be that this is a very disappointing talk, I hopefully won't be that. I also want to talk a little bit about determinism, because surprisingly, it's one of those things which seems to be surprisingly fuzzy in people's minds. People think of determinism and they get all sorts of weird notions. So hopefully we'll dispel a few of those. We're going to talk about a bit about the future direction of C++. We're going to talk about future disappointment in C++. And then we're going to talk a little bit, because obviously you guys are all practitioners and you all do your C++ every day, I would assume, most of you, or except for those who do it as hobby. We all want to know, can you achieve this stuff now instead of, say, 2026? And we'll be able to talk about what library facilities and other things we can use to get around that. So the first one is, for you guys who are stuck on C++ 11, which is probably, I guess, about half of you, I would say at least. You've got system error that's built into the standard library, so you can use that. If you are feeling a little bit risque, you can use a standard proposal, which is P1028. Came out with the SG14 low latency study group. You had John McFarlane here a few months ago, and he's from that group as well. So that's C++ 11, but that's more bleeding edge. And then finally, my library, Boost outcome. Okay, so what is disappointment? So this is something that's come up quite a lot. Who here doesn't know the difference between wide and narrow contracts? 1, 2, 3, 4, 5. Oh, about 10. Okay, in which case I shall explain the difference between narrow and wide contracts. So this is something which most programming languages have got very excited about recently. C++ is no exception. You'll find a lot of committee time has been spent the last few years talking about when should we do narrow, when should we do wide, and so on and so forth. So roughly speaking, a wide contract is something you can recover from. So when you give a wide contract to a function, you are saying that those of you who call me, I give you the facility that if you call me wrong, that you can recover from it. Whereas a narrow contract is saying that if you call me wrong, I kill you. And I really do mean kill, as in process ends, all stop. So most recently, C++ 20 has just added contracts into the language. That lets you mark up each individual function to say what its preconditions and its postconditions are. And if those preconditions or postconditions are violated, you can tell the compiler either just assume that will never happen, in which case we go off into undefined behavior land, where we just run off the end of a if statement that's never been compiled, and you just go off into random gobbledygook. That usually produces a seg fault. Sometimes it does not. Otherwise, you can also have a checking situation where the compiler will go off and check each one of these preconditions and postconditions, and if any of them are ever violated, it simply terminates the program right there and then. So that's coming. And that would be an example of a narrow contract. Obviously, you can also do, the interesting thing about wide default contracts is that you can convert them into narrow contracts by your code calling the wide API. All of the POSIX ones, or the system calls, tend to be wide APIs, because generally speaking, if you call an operating system function, you don't want it to kill the entire machine if you call it wrong. You generally want it to come back to you and say, you called me wrong. So that would be usually why most of the time they're wide, except occasionally when there aren't. Sometimes there are some narrow contracts functions to the kernel API as well, where, I don't know, panic would be the classic one on Linux. So if you call panic, it's game over. So that's an example of a narrow contract. So you can wrap these things up and you can convert wide into narrow, and that's become quite commonplace. So if you try to read a file and the file is not there, you simply say, well, game over, kill the program. So that would be a wide to narrow. The main difference probably is, oh, look at that. That is not good. Look at that dot going very, very slowly. Okay, so that's meant to be like smooth and fluid. So you have to be a bit more patient. So anticipated versus unanticipated exceptional failure. So generally speaking, an anticipated likely failure tends to be a wide contract. If it's an unanticipated failure, i.e. exceptional, generally it's often wide/narrow. Increasingly new code would try to make that narrow. But there's still an awful lot of code out there that simply throws the exception when it comes to a situation where it's exceptional. And you simply say, I give up. So throwing a std logic error or would be a classic example. The other, of course, is bad alloc. So how many programs can recover from running out of RAM? Not many. But what you do there is simply throw a bad alloc and hope for the best. Okay, so yeah, the anticipated versus unanticipated difference is probably currently the state of the art for writing new modern C++ code bases. And if you look at the file system library, which just entered C++17, and the networking TS, which might enter C++20, it's currently looking like it might actually be 23. I'm not actually up to date with what happened with that. They had to do some emergency meetings to try and get it into 20. But it might just be that they're just too hard and they might have to push it back. Either way, both of them have been written using this anticipated versus unanticipated difference. So here comes my mouse pointer again. I borrowed these two functions here out of the file system TS. I really rag on this function. You'll see why in a minute. I don't like it. Copy file from to, and down here you'll see there's an overload. Copies from to, and there is an L value reference taken error code EC. So how many people are familiar with this out of the file system? Just one person? 2, 3, 4. Okay. None of you are all that familiar with Boost file system? Because it's exactly the same, more or less. So Boost file system was been around for years, and they've simply put it into std file system. They changed a few of the constants and a few of the enumeration names. Other than that, pretty much exactly the same, including this terrible, terrible API. So here's the reason why I really don't like it. Would anybody like to take a guess what the bool here means? So you'll see there's a bool being returned. Who would like to take a guess?
To see the thing if the destination file has been existed or not.
So you reckon it would be that the file may have existed or not? Not quite?
So tell me if it has worked or not. That's it is a successful or failed.
So he says it'd be true if it's successful and false if it fails. But the top one throws an exception, right? Yeah. Oh, no, it's okay. I'll give you the answer in just a second. And then the bottom one has an error code return, right? Which would get set if surely it failed. So why has it got also a bool coming out of it?
That's because it's the life, so it shall have something wrong. Like that.
Okay, so if everything goes right, it returns true in both cases. And in the first case, when something goes wrong, it throws an exception and never returns false. And in the second case, it will return false plus filling your error code.
These are all possibilities, aren't they?
Are, yeah.
Would you say, looking at this here API, would you say that it's intuitive and immediately speaks to you exactly what it does?
Well, to each and all of us, it speaks in its own way, doesn't it?
Exactly. And this is why I really rag on this API, because it's not intuitive. You look at that and there's at least 4, 5, 6 different interpretations you could put on that, which are all totally matching the API spec you see in front of you. This is bad API design. And I know Beeman, if he's watching, I'm really sorry, because it was mostly him who came out of it. And by the way, this all went through a Boost peer review. So back when Boost file system went through 3 different times, through 3 different Boost peer reviews. And they still did this. And it just irritates me. It's stupid. But it gets even better because C++ committee came along and decided to make it even worse. So I shall now explain what happens. So I've added in a comment at the top. So up here, it disappoints always via exception throw. As a result, it always returns true. Always. Yay! Totally useful that. Because, you know, why isn't that void then? But anyway, let's just worry about that anyway. The second one's even better. So for anticipated failure, it disappoints via the error code. So it sets the error code to being an error code return, and it returns false. If it's an unanticipated failure, it disappoints via exception throw. So what do you think is anticipated failure and unanticipated failure? Can you tell from looking at that API which failures are anticipated and which ones are not? Do you think the C++ standard tells you which are anticipated and which are not? Actually, it does, but it will take you some minutes of parsing through about 3 to 4 pages of standardese before you have to join all the dots together, collapse it down in your head, and you'll finally come up with, oh, it does this. But it takes a bit of thought. I mean, it's not just there staring you in the face of what it is. So the people who designed this decided, for example, that bad alloc is an unanticipated failure. So that's an example where an exception throw occurs. If, on the other hand, it's out of disk space, that is an example of an anticipated failure, and so it's returned via the error code. And there's a series of other things. So all the other errors that could happen, some of them happen this way, some of them happen that way. All of that's part of this function's contract. If you're using this function, what you really ought to do is read the entire list of all possible failures and map out which ones go and throw and which ones don't. And you know what you're going to do? I can tell you what you're going to do because it's what I would do. You'd say, sod this, I'm just going to use the one that throws all the time. Yeah, because it's simple, right? Why bother using that second one? It's such, it annoys me. This, by the way, came in with the C++14 defect report. So originally, the original plan was that the second one was going to fail only through error codes, and that was going to be nice and fast, and that'd be deterministic, and it wouldn't have any throwing semantics whatsoever. Then some bright spark in the committee said, oh, no, we can't do that. No. No, we should make the second one throw exceptions, but only for some failures, and return the error code only for some other things through no particular choice of what's anticipated and what's non-anticipated. I got really annoyed about this, and I sent a whole lot of very angry emails to various people, and of course, nobody listened. So it is what it is.
Assume that the second function will throw only for the error conditions that are not covered by the error code.
So the question is, will the second function only throw for error conditions which are not covered by the error code? The answer is no, it does not. It throws for some things which are covered by the error code. Just because somebody in the committee came along, and I can tell you what happened there at LWG, and simply said, well, these out of the possible error codes, the POSIX error codes came back, we're going to say this one's exceptional, this one's exceptional, this one's exceptional, and these other ones are exceptional. And the rest we're just going to simply say they're unexceptional. And it was just totally arbitrary like that. The thing is who's that person to decide for you, the user, who's copying a file, what's exceptional and not exceptional? Who is it? It's just arbitrary, and it makes no sense. And it makes that second API way, way harder to use. And in fact, you're just not going to use it. Nobody's going to use it. They're going to use the first one. They're going to catch the exception that gets thrown and deal with it there, is what they're going to do. So that just annoys me. But on the other hand, you're going to find the networking TS is full of exactly the same pattern because they decided to make it homogeneous across the entire standard. So now all of your networking functions, some of them may throw some of the time for certain types of failure. Other times they will fail using error code using other types of failure. Totally arbitrary, which sucks. Okay, so what is determinism? The reason why I have to go and kind of actually explain this is because this is remarkably badly understood, even on the committee. So the committee's got about 120, 140 people, sometimes 160 people turn up. Of them, I would say about 40 actually have a good, accurate notion of what determinism is. An awful lot of people get it badly confused. Even on the SG14 low latency study group, which is a study group dedicated to determinism, there's actually a few people on that group who don't understand determinism either, which is not good. I won't mention who their names are, though. So the first thing is, it is not, and I repeat, not amortized predictability. We have this horrible, horrible problem in C++, mainly due to the terrible design, which is the STL containers, which are terrible. But unfortunately, at the time when they were designed, people thought to themselves, well, malloc is really cheap, because it was back on a Pentium 1. So we'll just assume that it's zero cost relative to everything else. And we'll just assume that when we're using this particular thing, amortized complexity is all that matters. And that's great. But then, of course, up came, what was it? Intel Core 1, I think, was when we really began to notice that malloc is really, really slow. And more importantly, malloc could not be made to go quicker, past what it was in Windows 7 or so. So malloc is now slow, and as a result, your amortized predictability is really not determinism anymore. Nobody could claim that it is. I also have to repeat, it is not, and I repeat not, anything to do with means or averages or medians. If you're thinking in terms of average of anything, you are not thinking about determinism. That has a very specific meaning, and I decided to just throw in two meanings, just to annoy people, because it's one very specific meaning. The first meaning, and this is the classical one, is the worst possible execution in time or space. So this is the worst possible. So if there's electromagnetic radiation pouring out of the sky and someone's giving it a terrible power supply with lots of peaks and troughs, what's the worst possible performance you get out of it? And that would be the classical one. Of course, we all aren't working on such systems. Those are mostly military and avionics. So we mostly work on non-real-time systems in terms of non-hard real-time. So we have to use a statistical approach. And I'm going to apologize to people in the maths right now, because of course, anyone who is keen on maths will recognize that these are the wrong percentages. And the reason why I say 2 to 5 sigma, and I use these are what management does. I have a management degree. So in the stats, in the management degree, they went and put up these percentages. I'm like, well, I already have a degree in computer science as well. So I put my hand up and went, those are the wrong percentages. And the stats teacher went, no, they're not. And yes, they are. So if you actually look up what 2 to 5 sigma is, those are not the percentages. But they are very easy to remember, and I will grant you that. So I ended up using that. So all you have to remember is 2 sigma is about 95%, 3 sigma is 99, 4 sigma is 99.99, and 5 sigma is 99.99999. Okay? So if your result that you're testing is below 99.999% of the time is below some bound, then you can say that it is deterministic to 5 sigma if it's that. So let's have a look at a graph which goes and shows this. So I decided to go off and randomly memcopy a 4 kilobyte chunk from a random location in a 100 megabyte region of RAM on an Intel Haswell CPU. I think the Linux was 3.15 kernel or something like that. And it's probably a bit more noisy than it should be because it's actually my home Xeon server, which it's got so many cores and whatever else, but it does all of the internet, stores ZFS array and a number of other stuff. So this is probably a bit more choppy than it really should be. But you can kind of get the notion there that the lower bound is around about 90-ish in terms of nanoseconds. And you can see there's some really big peaks up there, but most of the time it's kind of between 90 and 100. Yeah? So that's your measurements. So let's try sorting them, because that's much more handy. So that's the same data, but sorted. And you can see it's a lovely, nice flat curve. So you can see there that it's running along and it begins to taper upwards, and you get that standard power law distribution where it goes flying up into the sky at the very last sample. And if you calculate the numbers in that, here's your sigmas. So the median is 94, mean is 95, very, very evenly distributed. There's no slant or tilt in the normal curve. 2 sigmas this, 3 sigmas that, 4 sigmas that, and 5 sigmas that. Notice there, that's like 3 microseconds. And the mean is 0.1 microseconds. So you can reasonably say that this thing is deterministic up until about 3 sigma, 99%, because 108 is not far from 95. But once you're getting past that, no, it's not really very deterministic at all. This is a classic example of memory latency, because you have to bear in mind, on a system that's running, you're going to have task switching going on. So every now and again, your process is going to get interrupted and task switched to some other process. At that point, the latency will go much, much higher. Things might get evicted from the caches by maybe an interrupt came in. So this is what happens with non-hard real-time systems. You can only ever say things about determinism in a statistical sense. And most people are probably fairly happy with 99.99% most of the time. 4 sigma, probably fine. Okay, any questions about that? All makes sense? So the question is now is how do we get disappointment to occur deterministically? So I'm going to suddenly stop talking about that and branch off to something completely different. Who here is aware that there is a direction group for C++? Who sets the direction for C++ in the future? One person.
I think there's no direction.
Oh, have we got 4 or 5 or 6? Cool, right. Yes, so this was only founded last year-ish, I think. And it has Beeman, who's very famous, been on the committee for a very, very, very long time. Howard Hinnett, he is a legend. He came up with the datetime library. He is a maintainer for libc++ for years. Bjarne, I hope I don't have to introduce who he is. He, just in case you don't know, he invented C++. David, he worked for Edison Design Group. He's one of the people who makes the front ends for many of the main C++ compilers. He's also very, very senior. And Michael is Michael Wong. He was formerly the lead of ISO C++ in Canada for many years. It's back when I met him, back when I was working at BlackBerry. He's got a finger in lots of different pies. He does heterogeneous compute. The guy is just multi-skilled. And anyway, those anyway are the 5 people who are currently setting the direction for C++. So the document up the top, 939, is the direction document. If you want to go see what the direction is for C++, you can go get that link. It's a very long document with lots of different levels, like what's the scope at 20 years, 10 years, 5 years, 2 years, and so on and so forth. I'm just going to quote from the very front of the thing. So C++ rests on 2 pillars. This is actually from Bjarne's book, Design and Evolution, or whatever it's called. I can't remember its exact title. But the 2 pillars are a direct map to hardware and zero overhead abstraction in production code. Apart from these, and the language is no longer C++. Over the long term, we must strengthen these 2 pillars. Better support for modern hardware, more expressive, simpler, and safer abstraction mechanisms without added overhead. I've slightly paraphrased. I had to chop some sections out to get it to fit onto a slide. But that should have gone back. Nope, wrong way. Oh no, that's not good. Oh, it's trying to print it. That's very funny. Okay. Okay, so the reason I bring this up is because there is an increasing perception within the C++ leadership and the committee that C++ is moving too far away from the hardware. So you can now write a C++ program, and you're not really extracting out the maximum performance of the hardware anymore. You now have to write C++ in a very specific and very non-C++y kind of way in order to get the maximum out of the hardware. Most game studios will know what I mean about this. The stuff that you're writing is usually a subset of C++. You have to follow a very specific set of rules. This is beginning to worry the leadership because obviously we've got upstarts like Rust coming along and trying to go and supplant out of C++. So there's a push to try and take the low-hanging fruit in terms of the gap between the language and the hardware and fix it. And this is going to take obviously decades to work on, but you can kind of guess where I'm going to go next. So future disappointment in C++. So I should probably quickly mention history of C++ exceptions. I pulled this guide from a paper by Bjarne written, I think it was 1991 or something like that, where he literally called it History of C++ Exceptions. So even back then, it was necessary to summarize the history of C++ exceptions because nobody knew, and that was back then. So it was added to C front in 1992 by HP. Yeah, say that there was consensus building, would be putting it mildly. People wanted to add exceptions to C++ as early as 86, if I remember rightly. And each of the different formulations that people came up with, people didn't like them, various people objected. Eventually, I think HP just kind of got sick of it because they really needed them, and they just went ahead and implemented it. And then basically sent a huge patch set into Cfront and said, hey, we've implemented exceptions, and it's going to look like this. And then came the consensus building, and they eventually got it through. So the C++ exceptions you see today, they weren't part of the initial language. Bjarne felt at the time that he wasn't sure what he should do, or rather what he shouldn't do for them, up until eventually when something came about. And in the end, one of the hardest parts is what to prioritize about your exception handling mechanism. Do you go for speed? Do you go for flexibility? Do you go for scalability? And they decided that they were going to make these assumptions. So they're going to be primarily used for abort, so not resume. So one of the biggest things that was holding up C++ exceptions back in the day was that a large number of people wanted the ability to resume execution after an exception happened. So the exception would occur a bit like a signal handler. You'd stop, you'd look at the problem, you'd fix the problem, then you'd say back to it, it would carry on. And a number of people really wanted that, and eventually the decision was taken, you're not having it. So that's that, axed. The other decision was that they should be rare. So it's very important that they should be rare. So exceptions should almost never get thrown. And that we kind of accept. But what they didn't really think about at the time was what happens to control flow when you throw an exception. Because when you call a function, it's usually written down what can happen to control flow after that function returns. With exceptions, the control flow that can happen after an exception is thrown is usually not written down. You, the programmer, has to sit there and trace through, oh, if this happens and an exception gets thrown here, then this particular destructor will get called here, and that will then change this. That will cause the sequence of different things to happen. It's not written in front of you. It's something you have to deduce. And some of the bugs that are most heinous to go and find in a code base are exception safety bugs. If it was not written by somebody who was really good at exception safety, they end up writing really buggy code. And the trouble is because exceptions get thrown so infrequently, you never get to see the fact that these things get thrown, except in the particular cases that you're testing. These are a bit of a problem. Nevertheless, at the time when it was decided, of the different trade-offs that they had, it seemed to be good to go with these particular things. And the paper that I mentioned, I think it's literally called The History of C++ Exceptions, is written by Bjarne to justify the choices that they made and why they made them leading up to the present design, which is one that we currently have, bar some minor changes. And it's kind of interesting that he felt that he had to do that because I'm just going to see what's coming with my next slide. Yes. Because obviously it was contentious at the time. Okay. So when they say zero overhead, it's interesting. There's a camp of people who say, well, it inhibits optimization. So if you mark all your code as no, except you just simply turn off C++ exceptions altogether, you'll get much higher quality code gen. That's an argument. Some people feel that this is figures that Herb came up with. So Herb did a straw poll of different C++ user groups to try and figure out how much bloat was added to the binary by turning on exception handling, and it's anywhere between 15 and 38%. A lot of games turn it off as a result. Embedded programmers almost always turn it off because they can't be affording to expend ROM space on EH tables. Just turn it off and do without. And here's the other thing. They're really slow for the throw catch sequence. So I will just give you some figures of what that would be. So this graph is lies. I'm going to tell you that straight out. Plain out lies. Benchmarking that stuff is virtually impossible. So this is lies. Just assume it's completely made up and make believe. But just in terms of orders of magnitude scaling, the red dot, the red column rather, is for no error handling whatsoever. So we are simply calling code and it's never ever has any possibility of failing, never can happen at all. The light green one is where we have error handling in place, but it is not failing. The dark green one is where the error handling is in place and it is failing. And the yellow one is what happens if we throw an exception and catch it. This is, by the way, a log graph. So this is going up in units of tenfold. And up here is about 30,000. And as you can see down here is about 100. Right? So I think it's reasonable to say that an exception throw and catch, am I right in thinking that 30,000 divided by 100 is 300? 300-fold slower. That's a lot, yeah? It's a lot. Now, that graph that I showed you just before was actually for outcome, I should mention, and not C++, these putative Herb's exceptions, deterministic exceptions that I'm going to speak about in a minute, just to make that clear. Because we don't have any of those yet. They're purely abstract. But we do have outcomes. That's why I was able to give you the figures. So just to finish off this section on C++ exceptions. A lot of C++ coding guides ban their use. Google, a classic example. You go to a lot of main multinational corporations, and they simply say you cannot use C++ exceptions in this company while you work here. Or else you have to go and get an exemption from a really long bureaucratic process that's just not worth doing. It's one or the other. They usually go for the latter because they don't like to tell you no, but they're telling you no. The reason why is because the value added is not really worth the cost in terms of substitutability of programmers. So what I mentioned there beforehand, that getting programmers who are really good at writing exception-safe code, they're quite rare and they tend to be quite expensive. If you want your C++ programmers to be, you can get rid of this one and replace it with someone else who's picked up off the market. You want them writing at the lowest possible common denominator of C++. That's God's honest truth. That's what they're thinking. So they're looking to go and get you cheap and make sure that you never write anything that's too hard to go and maintain after you're gone, in case they have to get rid of you or you leave. So one of the quickest and easiest ways of doing that, simply don't allow anyone to write C++ exceptions, because they're hard. They also involve extra testing for all of those extra control flow paths that might happen. And there's lots of different corner case bugs in there because all of those multiplicity of things can never get fully tested. So there's lots of reasons why they simply ban them. The trouble is that exception-safe C++ is compatible with exception-unsafe C++, but exception-unsafe C++ is not compatible with exception-safe C++. So for example, STL is exception-safe, but you can't use it from an exception-unsafe code base like Qt, for example, because if you throw exceptions through Qt code, it may work, it may not. I noticed there that recent versions of Qt have a series of things where they say you can definitely throw exceptions through this bit and in these circumstances, but otherwise you can't. And again, you have to kind of look up the documentation and decide what you can do. These are one of the many reasons why there's no STL in most games. EA do their own STL, which is completely exception-free. And that's the STL that you're going to use if you're going to use one. And it's kind of a bit weird. There's lots of stuff that's different in it. You can't just take an existing C++ code base and use the EA's STL and expect it to work without porting it. So this has ended up with these two islands that separate. So there's exception throwing C++ and then there's non-exception C++. This is something which some people feel needs to be changed. One of those people who wants to see these things change would be Herb Sutter. So Herb is a convener of the WG21 committee. He has been for a very long time now, except for when he took a short break. He's head of C++ at Microsoft. You've probably seen talks by him. He has a blog, he's written books, so on and so forth. He's been around for a long time. That's the name of the paper. It's 709. It obviously caused lots of ruckus in the community when he published it. And he wishes to change how exceptions work. So his proposal is that we're going to have a new alternative exception mechanism which works in parallel to the existing one. This one's going to be value-based instead of type-based. So you're going to throw values of std error. So that will be the only thing you can throw if you want to use the new mechanism. You have to throw std error. That's it. That's the only choice you have. Std error is a type that's defined to be no more than 2 CPU registers in size. You can thank me for that one, because when Herb showed me draft 1 of his paper, I said, Herb, you need to make this thing really, really, really small so you can put it into a stack frame. So when you're unwinding the stack after one of these exceptions has been thrown, you want to carry this thing with the stack frame with no memory copying, no memory allocation. 2 CPU registers should do it. So that's why it's 2 CPU registers. And by the way, note that std error code happens to be exactly 2 CPU registers. So I just mentioned that because it has nothing to do with anything, but equally it might have lots to do with everything. So you have a choice in your code if Herb's paper were to come to pass. You can throw exceptions via the old or new mechanisms. That way all of your existing code keeps on working. But if you want to throw exceptions much, much quicker, i.e. 300 times faster, you can use the new mechanism. There will be, by the way, a compiler switch. So the compiler switch can switch your compiler to emulate old exceptions using the new system, but it's a backwards binary compatibility breaking option. So you'll find that all of your old code will still work, but it won't be able to link against any of the code that was compiled before. Now, this is the one that really caused lots of problems. Herb proposes that we get rid of unrecoverable exceptions, and specifically, he's talking about out of memory. So bad alloc and logic error simply cease to exist. If you ever throw them, the process terminates, and that's the end of that. It's a contract violation is what he's proposing. To say that that's been controversial, be putting it mildly. Lots of people don't like the idea that where your code used to be able to throw a bad alloc and you used to be able to recover from it, that now it's game over. Yeah, you should see the multinational corporations that when they saw this and how they reacted to it, it was very funny. Lots of very interesting private emails going, this would break our very popular, well-known piece of software, which I will not mention the name of. You can't do this. And Herb was like, yes, we can. So, you know, I'm the convener of C++, you know, plus I can do what I want. But anyway, no, it wasn't like that. No, we explained through how, in fact, their lives and their world would be much better if out of memory did terminate the process, because probably that was actually happening all along anyway, and they just never really realized. So the idea is anywhere in the STL, which is not no except at the current time, due to the potential throw of bad alloc or logic error or any of these other exceptions, is going to become no except. And all the stood error code overloads that you kind of saw earlier, the ones that are kind of stupid because they can throw as well as return error codes, would go away, which would be amazing. Okay, so I put up some code here to show Herb's paper in action. So if you notice here, there's a brand new keyword called throws, and I put it into green. And this says this function is working under the new error handling mechanism. And you'll see it's down here on this function as well. So you have to opt into this. And here we are throwing an arithmetic error C divide by 0. Now, the reason why this enumeration works is because you've set up a conversion. So you've told stood error that it can be converted or constructed from this particular enumeration. And this enumeration will be something defined in your program. So what you can do is you can simply say, if j is equal to 0, divide by 0. You can see here all the logic, the different errors could possibly pop out. And then if at the end, you can say, here's the successful result. Down here is caller, and caller calls safe divide, and it simply does what we did before. Nothing particularly different in that. Here's a bit that calls a particular code in question. Notice up here, we have no throws. So this is actually throwing type-based exceptions, the same as current C++ does. So here we call try, and we call the safe divide that we had from the previous page. Because there's now this stood error, we now catch a stood error E. There's no way of catching it by type, so you have to compare values. So the E was some arithmetic error C, and those will be able to map via the semantic comparison operator equals onto some error C enumeration, and you'll be able to compare them because they map automatically. By the way, this is already in C++. This is already in C++ 11. So this is actually a facility that's already there. So we're just simply reusing it for this. And you get down to the end here, and if you haven't managed to match any of the errors, you can throw a stood system error, which is throwing the same exception as a type-based exception.
Are you saying that because caller 2 doesn't have throws, it's using an old word, a different kind of safe divide for those types?
So the question is that because this caller 2 does not have throws on it, is it using the type-based exception throw mechanism? It is. Your then second question was, is the safe divide that it invokes a different safe divide? And the answer is no. Safe divide was marked throw, so it's under the new exception handling mechanism, and it will throw and catch using that mechanism.
But what if no exception escapes from caller 2?
So the question is what happens if the new type of exception, the new type of exception escapes from safe divide and goes out through caller 2, is what you're asking. Well, what happens then is that there is a well-defined mechanism for converting between stood error types and the legacy type-based throw system. I think Herb talks about it in his paper somewhat of exactly what the semantics would be there. So that's defined, that works. There's a question at the back, was there? Yeah.
So we saw the value in integer, right? Two registers, that's 64 bits, right? What if I cast a pointer in integer, I just throw the pointer?
So the question is what happens if you cast a pointer to...
The reason is I will be just throwing an instance of an error class via pointer, via integer.
So the question is what happens if you'd be throwing a instance of an error class by taking the pointer, casting it to an integer, and putting that into stood error? You could do that, but you'd want to be on a 32-bit system, I'd say. Or else you make sure that you allocate your type below the 32-bit boundary, or whatever your int happens to represent. Or you can have a global array. Yes, yes, you can.
No, I'm just asking in terms of how you can twist it in that way, and break the whole idea.
Oh, sure. So the point is that you can twist it in this sort of way. And of course, because we're C++ programmers, we would do that. There are people who manufacture system categories by dynamically allocating them with custom defined virtual tables in order to create payload attached to arbitrary stood error code instances. Just because you can doesn't mean you should, but people do. And where you're able to do it, people will go there. I agree that the handling of payload is an interesting problem with Herb's current revision that's currently published as his paper. I'm not going to say too much more, but his R2 of his paper goes into a bit more detail and tightens up some of the language and the definitions on that. So it's in progress. Any other questions? Okay. Actually, no, oh, there's the time. No, it's not the time. Just checking. Yes. Yes, go on.
Does the paper covers the static analysis? Like, does it cover the case when you want to know if this function throws?
Does the paper cover static analysis? So if you want to know if the function throws, indeed it does. There is a throw inspection function which works very like no except, and you can inspect a function to find out if it throws into the new system or not. Also, you can define whether the thing throws into the new system or not based on a context per expression. So you can actually create functions which may throw onto the new system or the old system, which generated and interpreted at compile time. Fun, 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 huh? Of course, it's C++. We have to be able to do all that stuff. Okay, so summary of Herb's paper. Opt-in value-based throws replace table bloat with fatter, cache-heavier code. Because you see, if you take away the tables, you simply pad out the code that's being generated because it now has to have more tests in it, more branches, more whatever else. It gets fatter. Question is, which is more optimizable, foldable, etc. So I think it's fairly public knowledge that there is a prototype compiler that's going to be built to implement Herb's exceptions, and we're going to find out because nobody can actually say. Lots of people from all the compiler communities said, no, tables will be better. Other people said, no, it'd be much better to go the other way. Reality is nobody knows. Even the compiler vendors who've been doing this their entire lives, they all have reasonable guesses, but until we actually build a compiler, compile Linux with it or something, we won't actually know, although Linux wouldn't help because it never throws exceptions. All right, STL or whatever then. What I would say, though, is that Herb's proposal, if it were to be accepted, makes the STL much less throwy. And the other thing is that deterministic exceptions become effectively as lightweight as control flow. Kind of pretty obvious that if they are as lightweight as control flow, they're going to be used as control flow. And that kind of countervails all of the teaching we've done in C++ for years that do not throw exceptions as control flow. Well, if they're exactly the same as, people are going to go there. Of course they are. And it'll be interesting to see what happens. I will say that there is still one issue with Herb's paper, and it's control flow inversion. So I mentioned earlier on about how if you have code that can throw exceptions, that all of this stuff is unstated of where the switching points are, where an exception could come out to this particular point, where control flow might go next. All of that's still unstated. I think that's unfortunate. A lot of other people would really like to be able to say in the code, here is where an exception can be thrown. When you're auditing the code, you can say it comes from here, and you can reason with it in your head at the time. And it would be really great if the compiler could actually say, you must put in everywhere where an exception could be thrown in your code, and that way then you can see it, so you can audit it. Obviously, opt-in, not turned on by default. So that gets onto a paper by me, yay. So N2289 is the code for the C committee, so that's why it's one code, and then 1095R0 is the one for WG21 C++ committee. So I sent the paper to both committees. That's because it was developed by both committees in parallel and in tandem. And I'm the lead author, but there's dozens and dozens of people who've had feedback into that paper, and they're listed in the acknowledgements. So what it does is it takes a slightly different tack from Herb's proposal, which is mainly focused to C++, and instead comes at it from, well, let's just change C. Because if you change C and C++ has to remain compatible with C, then you change C++ by changing C. And more importantly, if you change C, then you change Rust, and you change Python, and you change Go, and you change every single thing that speaks C, including POSIX and Windows and everything else. So let's just go big or go home, yeah? Why not? Let's just add exceptions to C. Why not? Now, I went and originally pitched this to WG14. I said, yeah, can I kind of like add C exceptions to C? And surprisingly, they went, yeah, why not? And I went, really? Are you joking with me? Because, you guys aren't exactly known for, embracing really radical changes to the C language, which is pretty much unchanged for like 2 decades, 3 decades. They were like, oh, no, we've been discussing this for like 2 or 3 decades, and we've got really formally decided, ideas about how we should go and implement exceptions in C. I went, really? So I talked to a guy called Doug Gwynn, who's been working on this for about 30 years now, and he came up with the stuff that he definitely didn't want to do, and the stuff that he did. And lo and behold, we now have a paper on it. So we've made it compatible with Herb's exceptions, and the convener of WG2014 was very good at, bridging between the committees on this stuff. So basically, we take Herb's thing and we just push it into C, and via that C++. Okay, so here's how it works. For C functions, you're going to be able to mark them with a thing called fails. And the fails takes a type to say, this is the type that I can fail my C function with. If you mark a C function this way, then the calling convention for calling such functions changes. It now, under the bonnet, returns a union, and the union is of the declared function type and the failure function type. Discriminant, which says, are you a failure or are you a success, is some unknown, who knows what, architecture determined specific thing. Something that's lightweight. It's not something that's stored with the actual union. My suggestion in the paper is the CPU carry flag. I thought this was a great idea because, there's actually some precedence for using this. Then people came along and went, oh, RISC-V, the new CPU architecture, doesn't have any carry flag. I went, oh, is there another flag you can use? It's like, no, it has no flags at all. I'm like, oh, what? So I was like, okay, so we're not going to use just CPU carry flag. If you have a CPU carry flag, use it. If you're on some weirdo architecture like this brand new one that's apparently the future of all CPUs, then do something else. And I suggest a register or whatever. Or even, do you know what they could do? Because they're still defining RISC-V, right? They could just add a carry flag, right? Or they could just add a fails bit, which has just been added in right now. If you're watching RISC-V people, just go ahead and do it. Makes life much, much easier. Pardon me. So fails functions are interesting. If you want to call a fails function, you must explicitly wrap the function call with a catch or a try. You might immediately ask, aren't these going to conflict with C++? And the answer is that these are actually macros. So fails is a macro, catch is a macro, and try is a macro. Before you all go, ugh, that's disgusting. That's actually the way that C does things. So if you look into std_bool, std_bool defines a bool macro, which expands into a capital _B bool. And exactly the same mechanism would be here. So fails is a macro that expands into _capital fails with an F. Same for catch, same for try. So that's how it's compatible with C++. And I'm just going to hand wave that one, and everybody just, accept it to be true. C and C++ do things differently. If it comes that this stuff actually gets approved, they'll figure something out that makes this stuff just work. So none of you will ever have to worry about it too much, I hope.
Sorry, if I have a function that calls another function that calls one of these failing functions, do I have to put a try catch in the intermediate callers?
So the question is that if you had a function that calls another function that calls one of these fails functions, do you have to have a try catch in the intermediate? The answer is that anywhere where you call a fails function, you must wrap it with try or catch, or the compiler will not compile it in the proposal.
So it's really equivalent to calling a function that returns a union, and you check your union and you get it back to see what you've got.
So the point is that, is it like a function returns a union and you call it get back the union and check to see what you've got? The answer is yes and no. So the answer is yes, that conceptually it does do this. The answer is no, because the compiler is doing stuff under the bonnet to make that more efficient than you could ever write it in C or C++. So for example, it will use some sort of discriminant. It also would understand the difference between fails and success code paths. So during inlining of code, it may break all of the success paths and just assemble them as one. And then it may put all of the failure paths and do something there. In other words, because it understands the semantic difference between the two, the compiler can optimize that with the full knowledge that this is a success, this is a failure, rather than having to guess from the code that you're feeding it. So that would be the answer. We hope. We don't know until we've built the prototype compiler, of course.
But you don't get that lovely thing with throwing exceptions where you just call a function, goes down, 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 and eventually it throws, and you ignore it, and then say catch.
That is correct. So the reason for that is that WG14 do not like auto-propagation in failure at all, and that is a red line, will never be permitted into the C programming language. So they really want the explicit point where you annotate these things where they could fail and what to do with them at the direct point of call. And in the end, that's where they're at. They think that the auto-propagation system that C++ uses is a major failure of C++, and there's a lot of very passionate views that was a huge mistake. So, and of course, that's getting into bike shedding. That's fun. Question back? Sorry, say again?
Rethrow.
Oh, rethrow? How do you mean?
Throw without anyone. Like rethrow the exception. Go back one.
Okay, so the proposition is a rethrow command. You shouldn't need it in C because you can never propagate. So the thing is, you actually use try in that particular circumstance, and I'll come to that shortly. There's a question just before you as well? No? Happy? Okay. Yeah, so try is in the Rust/Swift form, not in the C/C++ form. But we're going to change it so that it is like the Rust/Swift form if they accept these proposals. So that explains that. I'll get back to that. Oh, yeah, I forgot about that. Yeah. So, so we're going to solve Erno. So here's the trouble. Erno has been a blight upon everybody for 20, 30, 40 years now. Erno under POSIX is the global variable that gets set whenever a POSIX function fails. They had to change it to a thread local stored variable because otherwise you were corrupting your global Erno state, and as a result, multiple threads, you had no idea whether something failed or not because it was racy. The trouble now is with it being a thread local state that it still has side effects that's global and outside the function that called it. So in your C math functions, you can't do any pure common sub-expression elimination because each one of those could write Erno, and as a result, you just have to stamp out and call them one after the other. As a result, almost everybody who uses the C math functions disables the standard conforming implementation and turns on fast math, right? And this is the kind of thing that gets standard committee people really annoyed, because if everybody's turning on fast math all the time and is using a non-standard subdialect of the standard, then there's something wrong with the standard. Yeah, fair enough. Trouble is how to solve it. There's been paper after paper after paper over the last 4 or 5 years. They all have proposed to do something about Erno, and this is yet another one of those papers. But this one probably has some more chance of success because we're actually simply implementing the Erno solution using the failure mechanism that we just talked about, and it basically just goes off and it returns a struct of whatever the type of the function is and the int of the Erno. That way Erno never gets set. That means you can mark all of your C math functions as being pure, and yeah, performance gets much better, optimization, and this makes lots of committee people very happy. So it's funny, this paper, when it went out for internal review, everyone just came back and went, oh my God, you solved Erno. And I'm like, well, what about the rest of the paper? They're like, oh no, but you solved Erno. And I'm like, yeah. So we'll see what happens. I have to say, it was funny, WG14, so the C programming language committee, they were really happy to see this. I think it really bugs them, the whole Erno situation. I went before Austin Working Group as well to ask them what do they think about this for POSIX. And they read the paper and they only had one comment, which was, please use, for the ABS function I have in the paper, I give an example, please don't call that the ABS function because it might confuse it with the POSIX ABS function. Please call it my ABS. That was literally the only bit of feedback I got back from them. So it's like, so you like it then? And they're like, yeah. I'm like, oh God, right. So great feedback, you know. Hey, they didn't say that they hated it, I guess. So see what happens. Okay, so how does all this stuff fit into C++? Because obviously anything that you do in C is going to map into C++, so you're going to have some sort of equivalence mechanism. So what I'm proposing is that you can mark your now functions, throws, like under Herb's proposal, or you can have throws E with a particular type. Oh, that looks like a dynamic exception specification, doesn't it? Oh, that's terrible. It's not actually that. It's actually a static exception specification, which is not a dynamic exception specification. And I'm not going to talk about that because that so gets people worked up. Fails E, which is the thing we just saw from C, and then of course you have no except, or of course nothing. So those are the way you now will have 1, 2, 3, 4, 5 ways of marking up your functions. Oh, I bet you all love me. So if you mark up in C a function with fails E, instead of using throws E, then in that function, you now must annotate every call of a throws or fails function with try or catch. That solves the flow inversion problem I was talking about beforehand. A whole lot of people are really, really keen on this. They want to be able to see all the different control flow in their function, and it's opt-in. If you don't like it, you just flip the fails to throws. You're now back into the auto-propagation mechanism. Throws simply works by silently injecting a try. So the try operator is effectively implemented as if the function we just called failed or threw an exception, then I will propagate by returning and throwing the same exception from the function right now. So you simply propagate it down as it goes up the stack. Does that make sense? Everybody happy with that? Okay. So all you're doing is you're silently injecting it into normal code. If you're in a fails function, you have to manually write it. Okay, I'll just see what there is some time there. Okay. So here is your function from before, safe divide, but we've now implemented it completely in C, not C++, using fails. So as you can see, we're basically doing the same thing, but notice we have this new thing here called failure. So failure is the way that you return a failure from a fails function. It's also a macro, and it also expands into capital F, failure. Here, of course, there's no scope, because in C we have no ability to say arithmetic error C, because there's only standard enums, not class enums. So as you can see, otherwise than that, it runs down with the same logic. Get down here, this also fails with arithmetic error C. And you'll notice now that we have to wrap the safe divide in a try function. Okay. Here's your caller 2. Up here, whenever you call safe divide, you now have to wrap it in catch unless you want to auto-propagate it. Catch expands out into a designated initializer. Does anybody not know what a designated initializer is? Okay, I see 2, 3 people. This is a feature that was added to C17. How many people knew that there was a C17 standard? Oh, there's a few people. Cool. Yeah, no, C have been keep making new standards, same C++. You just don't tend to notice it very often because they never really change very much. But one of the things they added was designated initializers. So the idea is that you can initialize any union or struct by putting your curly braces, and inside there you put a dot, followed by the name of the thing you want to initialize, and then equals the thing. And you can just list out just the items you want to initialize in your designated initializer list. This is something that was added into C17. It's very nice. It means you don't have to write out all the things. You don't need to know the structure of the thing you're initializing. It's great stuff. And they've partially merged it into C++20. There's some cases that don't work, because why not? And there's no generic mechanism for overloading it yet. And I have proposed to somebody to go do something about that we do something to C++ to make that more generic. Either way, this structure up here is what will be initialized by, because catch expands out into some designated initializer list, and it will initialize some value member or some error member, and it will set some failed member. So that's all it is. It comes out as a set of brackets that initialize something other. So if safe divide is successful, it'll initialize value to whatever the value was, and it'll initialize failed to false. If safe divide failed, it'll initialize error to something, and it will set failed equal to 1, because of course C doesn't have any notion of true and false. It only has 0 and 1. And that's your underscore bool, which is the type involved there. Does that make sense to everybody?
I just didn't get the previous one. The previous example.
You didn't get the previous one?
Yeah, because you said it doesn't propagate, but it seems like the previous example is propagating.
So the previous example, the reason why it propagated was because there's a try down here. See?
Yeah, so you can propagate.
If you wrap it in try, it propagates. But you have to explicitly say, please propagate.
Okay, so
If you didn't put anything there, it wouldn't compile. So you have to say try or catch. And you're not allowed, by the way, in C, put expressions inside the try and catch phrase. I try to have expressions, but some people make these really simple C compilers. There's like 2 C compilers with people on the committee who have their own toy compiler that they basically maintained for the last 30 years. And they said, oh, we couldn't do expression evaluation in there, it'd be too hard. So we had to axe that. Question in the middle.
Well, then if we have 2 try statements in the function of the previous slide, what happens if one of them throws a arithmetic error and the other one throws some other error?
So the question is what happens if you had 2 try statements in the previous slide? You're saying not 2 try nested with one another, but 2 separate try statements. So if the answer to that is that if the type that gets failure is not compatible with the function that called the try, it doesn't compile. And in C, your error type is going to be probably some integral type, maybe a structure if you're very, very lucky. So yeah, C is easy. At the back? Oh, you want to go back to, yes. You mean the previous slide or? So the question is, the point is that this looks very ugly. Can you make it better? Yes, you can using macros. Yeah. So in the paper, I've defined a macro which will expand out into that, and it's a lovely. It's called failure with some stuff in the center of it. I think you take the T and the E, and it basically expands out. So yes, you can do it all with macros. Macros are great if you're in C because they're the only choice you got. So what are you going to do? Yeah, and so yeah, the logic that comes after this is dead simple. You simply go, did you fail? If not, then return the value. If you failed by this, return 0, and it's exactly the same logic as before. Happy? Straightforward? Looking forward to this feature in C? No? Okay.
It doesn't look like the typical way we use exceptions in C++. We kind of do logic in the first part of the large function, and at the tail function we have the sketch and all these types of failures. But in your example, we have to call function, then get failure and check it. Then we switch to next step.
Yeah, so the point that was being made was that in C++, what we tend to do is we tend to do a great big body of success-oriented code in the try statement. And at the very end, we'll have a catch, which catches for the entire all possible failure that happens beforehand. And he was pointing out that in C, it's much more bitty. There'd be lots of individual tries and catches scattered throughout the entire code. I would say that C Standard Committee views that as very much a feature and not a bug. So they consider that to be absolutely amazing, and what we do in C++ to be terrible and awful and tool of the devil. They equate it to being the same as Gotto exit. So that's what they view it as. So there's an exit label at the bottom, and we just always jump to it, is the way that C people do. And they, of course, Gottos are bad. So
even Gotto is better because you gotta you put all labels at the tail, like unwinding the failure state.
are you advocating in favor of Gotto?
Yes.
Oh. I tell you, I advocate in favor of Godot too, and I get in so much trouble for it. People have shouted at me over it. So I say sometimes Godot's the right solution to the problem. Sometimes it is. It's very rare, but very occasionally, Godot is just cleaner, simpler, straightforward, and then people get very angry.
It's everywhere in the Linux source kernel.
Oh, you're saying it's in the Linux source kernel? That does not surprise me at all. Python, by the way, uses lots of Godots as well in its core interpreter.
There's nothing wrong with it.
Nothing wrong with it. No.
It's okay to use Godot.
I learned programming. It was an assembler, actually. So for me, writing spaghetti code was just natural and normal, and why wouldn't you? It was only very much later on, because I could always edit my spaghetti code perfectly fine. The trouble was that I realized nobody else could, and that was antisocial and mean. So I had to stop doing that. But it's always easy to do code which pushes you. It's really hard to do code that doesn't push anybody, if that makes sense. And if you're nice and professional, you should probably be nice to other people. Just because you can doesn't mean you should. I mean, like a lot of Boost code, it's virtually impenetrable to 99% of C++ programmers out there. And there's a strong argument to say, that's not nice. You should make your code simple. I have now made a Boost library, and people keep telling me that it makes absolutely no sense whatsoever, and that's other Boost people. So they come along and they look at the source code and they go, what the fuck are you doing? This just makes no sense at all. There's a whole lot of stuff where you're jumping into other things. You have like ADL customization points that invoke other ADL customization points and recurse back in through your recursive template meta logic. And I'm going, yeah, and it's really maintainable for me. You guys aren't supposed to be looking at the implementation. I mean, I'm the guy who has to maintain this stuff over the next 20 years. I'm literally making it as easy for me as possible. So if I can get the compiler to automatically just go out and maintain itself by me changing one single template parameter in some obscure location, I'm going to do that. But I totally get that anybody else coming along to study that code is just going to go, wow. You know, and indeed that was a problem during the peer review because people are trying to study this stuff and they go, we don't know how it works. I'm like, well, it works. Produces really nice assembler. When you compile it with optimization, it just comes down to nothing. Anyway, that's getting off topic. So I'll push on before, yeah. Basically, if we can get this through, Rust, all the other languages, can start talking to C++ directly without any wrappers, and that'd be amazing, I think. Oh, and of course, C can now send exceptions to C++, which would be kind of cool. So for example, if you call a math function fails, that could pop out as an exception throw. Yeah, do we like that? Yeah, if you call the POSIX read function or the write function and there's no space on the hard drive, pops out as a C++ exception throw. Yeah. We like this, no? Okay. You see, that's kind of thing gets me excited. I'm like, oh, we'll never miss an error ever again because everything will throw all the time, all possible failure. That won't break any code. No. Okay, so I know time's getting a little limited, so I'm going to try and wrap it up. So if you guys kind of like what you're seeing, I've so far got the feeling that you really don't, but if, say, some of you decided at work that you want to go off and maybe implement some of this stuff into your code bases at work so you can get everybody in your team to hate you and probably make yourself unfireable because, you know, only you will know this system, this is how to do it. So the first thing is system error. It's really interesting. This came with C++ 11. It actually came out of Boost system. So it's been around since about 2008, maybe. So it's around. If you don't even have C++ 11 available to you, Boost system will provide stuff for you. It's probably the most commonly used STL header that nobody has ever heard of. Who had heard of system error before? 1, 2, 3, 4. So I'm right in saying that nobody's ever heard of it, yeah? Cool. Do you know why it's the most commonly used header that nobody's ever heard of? Take a guess. Would anyone like to guess why it's so commonly used? At the back?
That means I use a function there which throws the exceptions for the STL.
So
I had once a thinker who
the guess is that the STL might throw some things using it. You're pretty much correct. So it's really interesting. It provides the advanced error and exception handling infrastructure. And guess what? You guys are including it all the time. Because if you include array or complex or optional or any one of the other C++ 11 or later headers, you're almost certainly dragging a system header under the bonnet. And system error, which is just amazing, includes std string. When you include std string, it brings in all of the allocator machinery, all of the iterator machinery, and all the other fun stuff like codecs, right? So you're dragging in all the internationalization stuff just because you brought in system error, which is just because something nice and simple like optional, which should have nothing to do with any of this stuff at all, is dragging in system error because there's one location where it throws an exception using system error. Just one. So that's just stupid. It's another one of those examples of why you're dragging in about 40% of the STL for absolutely no reason for one single location where you might throw an exception type that possibly, if you pull its message, would return a std string, which is why I need to bring this. Annoys me. But the thing is, you can actually do something about it when you join the committee. You can actually come along and go, this is really stupid. And everyone goes, So here's how we're going to fix it. And everyone goes, no. And we'll see what happens. But I'm going to give it my best shot. For deterministic disappointment, we only care about a really small subset of system error. System error is a really big thing. Does lots and lots of stuff it really shouldn't do. And here are the particular functions you want to know about. So the first one I've mentioned a few times is std error code. It's really simple. Consists of an int and effectively a pointer. Reference, pointer, who cares? So all it is those two. It's really interesting as an integer and not an int pointer t, because that would be kind of way more useful, wouldn't it? But it isn't. So it's an integer. That causes all sorts of problems, like what was mentioned at the back there about cutting bits off of things you might want to store in it. Hey, it is what it is. Std.RC is just a simple enum of the POSIX causes of failure. And if you are in your code and most of the common causes of failure tend to be covered by the POSIX ones. So if you just need to return some error code, just borrow Std.RC and just use it because it's just there. It has all of the items you need in it. Std generic category is the category for Std.RC, and you can create an error code using a category. And if you use generic category, you're saying I'm using Std.RC as my error coding system. System category is for whatever your host system's error coding system is. So if you're on Windows, that's going to be the get last error coding system. If you're on POSIX, it's going to be error no. If you're on, I don't know, Plan 9, no, I think it uses POSIX as well. Some weird Amiga OS, say. I'm sure Amiga OS, I've never used one, had some error coding system, and whatever it would be, that would be, system category. And finally, there is the system error exception type, and that's simply the type that you wrap up an error code into if you want to throw it. So if you have an error code and you've decided I don't want to do anything with this, I just throw it in a system error, throw it, and it participates in the standard C++ exception system. Okay, yes, because I don't know if we're all a bit too tired to work our way through this, but I'll quickly do it, and hopefully if your eyes all glaze over, I'll just press on, okay? Okay, so here we have some function which writes some data from a buffer of this number of bytes, and it's going to return an error code to indicate what happened. Because our POSIX write function is one of those things that can early exit, we have to put it into a do loop. So here's the do. And what we do is we try to write out the buffer with the number of bytes to the file descriptor, and we get back the number of bytes that was written. The question then is, did this function disappoint us? If the number of bytes written was greater than or equal to 0, then we're going to increment the buffer pointer by the number of bytes that we just wrote and subtract off the end the number of bytes just written. If the error code was not E again, so E again is where it's a temporary failure. So let's just say it is a temporary failure. We're going to jump down to here, and we're going to see that bytes is still greater than 0, or maybe it isn't, in which case we're going to loop back up to the top, and we're going to retry the second part of write. And we're basically going to reiterate it for all those partial buffer fills until the entire thing is filled, okay? If, on the other hand, E again did not come back from error code, that means we have a real error. So what we do is we construct an error code with the error number that we just brought back, along with the system category, because that's what we have here on POSIX. And if it is an anticipated disappointment, so for example, if there's no space left in the disk drive, or maybe there's a permissions failure because we don't have write permissions to this particular file descriptor, then we're going to return an anticipated disappointment. Same as what I was mentioning earlier on with networking TS and file system TS. If it's an unanticipated disappointment, so it could be something like SIG bus, like you have a seg fault or something like that, then we're going to throw a system error with the error code question. Okay, there's one other minor little thing. Down here at the bottom, if we do get to the bottom, we return a default constructed instance because a default error code construction has the convention of no error here. Does that all make sense to everybody? Cool? Yeah, there's a whole load of problems with that code, and none of it's obvious. It's all very, very hidden. So at the bottom there, I mentioned that it has a convention of no error here. This is something that came up last year. Turns out that everybody who's using error code is using it wrong. And we estimated there's at least 10,000 projects out on open source land from a quick copy and search, and they're all using error code wrong. And people on the committee were like, oh, well, they shouldn't be using it wrong. Clearly, the standard says this. I'm like, well, who cares? The reality is most people out there are using it wrong. Why are they using it wrong? Because ACCU uses it wrong. The reason why ACCU uses it wrong is because Chris Kohlhoff decided that he was going to use it in a certain way. So all of the example script stuff in ACCU's documentation uses it wrong, so therefore comes through. And Chris, when I raised this with him, he said, well, everybody should understand how it works, right? I'm like, no, Chris, no, they don't. So here's the thing. If you test an EC, an error code, it's going to return back Boolean true if its code is non-zero. It says nothing about the category. The category can be anything. The code just has to be non-zero. If you do if not EC, then it simply means that the error code is 0. It doesn't again matter about the category or anything else. So the convention that 0 is somehow not an error is entirely dependent on your system's definition of error coding. You could be on a system where 0 means not, well, it could be a very serious error. It could be all sorts of different things. Who's to say that 0 should be failure or success? Unfortunately, we've ended up in a situation where that's the way it is. Even better than that, a default constructed error code is defined by the standard that must have system category. It cannot be a generic category, because if it were a generic category, we could define error code 0 as being success, and that would be a work around the problem. Anyway, we've raised this up with errata with the committee, and we're going to try and get that changed. I think Peter Demoff is heading that up, and there's a number of other changes that we're going to context-profy error code much more than it currently is, and hopefully we'll get that bug fixed soon. Cool. Okay, or rather than fixing error code, we could just replace it. So this is status code. The paper for it is 1028. It is also by me, but it's not by me. It's also by SG14. So this is one of those interesting cases where SG14 made out a list of problems with error code, and there were lots and lots and lots of them that accumulated over the years. And after they had voted on it, they all completely agreed that these are terrible problems and they should be fixed. I came up with something that solved all the problems. We then put it back before SG14 again. Everybody took a vote, and there was a unanimous vote to take it up to WG21. So it's currently standing before Library Evolution Working Group, and I would like to believe they're just going to say yeah and just say yes to it. Although they probably won't, but I'm going to think that they're probably going to. I mean, it's a no-brainer. And moreover, I've been using status code now in my own code for the last 2-3 months on a daily basis. It's just better in every way. I'm sorry to say, but it's just better. It's just correct. It's the way that it should have been done from the beginning. I'm not at all dumping on the people who came up with error code first day. At the time it was designed, it went through Boost peer review. It went through a lot of expert eyes looking at it. And a lot of people came down and said, yep, this is fine. There was quite a lot of confusion with error code back in the day that required Chris Koloff to write a 6-part blog post on exactly how error code works, because nobody could understand and wrap their heads around it. And this is even amongst the Boost community, right? So even then after that, I've noticed a number of WG21 committee members getting error code wrong. So when you looked at some of the N papers and the P papers that came up, they were misusing error code. They were using it wrong, just not the way that it works. And you'd have to send them an email and kind of go, yeah, I really don't want to raise this too loudly, but you want to go and read Chris Koloff's blog, the 6-part explanation, and then change your paper because your paper's wrong. And they usually do. So it's interesting that error code still confuses the hell out of everybody. But we're hoping that that can be made even more confusing and even harder to wrap your head around. And I say this because status code is really funny. We've inverted the template design in it. And to say that this completely befuddles the world experts in C++ would be putting as an understatement. Even SG14 members, after they wrapped their head around and went, yes, we're definitely doing this, this is great. It should be inverted because that's the right way around. You leave 3 months go by, they come back to it and go, why did we invert the template again? It makes no sense. I don't understand it. It's all the wrong way around. And I'm like, well, you all voted on it. You had a unanimous vote. But anyway, we'll see what happens. Probably going to get in trouble for saying that now after the video goes out. Anyway, yeah, so paper 824 is like 12 A4 pages, maybe more, of just problems with system error, one after the other, out in real world code base. This is worth reading, actually, because it really wraps your head around the problems that there are in such a simple header as system header. I will say, it only happened in hindsight. I would say that the assembler that pops out of status code is lovely. So I don't know if anyone knows this, but I view the C++ compiler as basically a glorified Mac assembler. So I don't really view it as a language at all. This gets me into lots of trouble. But when I'm writing programs, I tend to look at the optimized assembler that's generated output. So I mainly debug through that. So when I'm just ignore the C++, that's irrelevant. I'm looking at the assembler that comes out, and I'm stepping my way through that, and I'm counting the opcodes in my head as I'm running along. And that's the way I write code. So I'm very much the view that everything's assembler, and I just read everything through the assembler. So what I really like about status code is it generates really nice assembler. The assembler is logical, it's well put together, it hangs right. Stuff that comes out of error code is all wrong. It's all messy, and it's got things that shouldn't be there, like atomics, right? You wouldn't think that error code would call atomics, but yes, it does. So yes, we do have to initialize atomics, and we're going to do a sequential store at this particular point, and you can see the actual lock X add coming in there. And you're kind of going, why is that there for? And it's because of magic statics. So that's the reason why. Yes, and the thing is, it works perfectly well in exceptions disabled environment. So that's kind of handy, and it was deliberately designed around that. So here's the interesting part. This is where we're coming back to Herb's proposal. So P1028, the status code, happens to be implemented via typedef into std error, or a std error, which happens to be 2 CPU registers in size. It exactly meets all the stuff that Herb was looking for in this paper. So if this paper goes forwards, it has a reasonable chance of becoming the std error message, or type, or pardon me, value, even I make a mistake, that everybody's going to be throwing around the place in future C++. Maybe, we'll see what happens. And I obviously then also extended that out at P1095. Works in the C++ 11 compiler, new GCC 5, Clang 3.3, or Visual Studio 2015 or later. And I would point out it is experimental. You just don't know WG21 might change it. So that's another option. If you want to go and employ this stuff today now, you might get into lots of fun at work because you're like, using experimental, standards proposed libraries. But hey, it's there as an option. Okay, we're on to the final section, and I thank you very much for sticking with me so far. I can see some yawns happening around me, and people are getting a bit tired. I have to admit, I am also very tired. I had very little sleep this weekend. I had to do a server migration because my existing server had been installed in 2012, and it kept falling over and dying just because it kept being upgraded, and it just needed to be wiped. So I've been preparing this VM image for the last 4 weekends because I work here, but I live in Cork, and I come up and down every weekend. So I had to first suck it down, stay up until 5 o'clock in the morning, moving the VM image over onto the main system, finding the internet wouldn't come up because, of course, it runs inside a VM as well. And anyway, I won't bore you with the details. Either I did not get much sleep. So I am also looking forward to heading home to the lab. Anyway, here's Boost outcome. There is the link to it. This is an approved library. It's passed Boost peer review. It's into Boost. I just need the time to redo the documentation to match the changes that Boost demanded. But the code's been finished since like June. Lots and lots of people are out there using it already. I get so many bug reports. I know that Microsoft have deployed it en masse into their IoT stack. So all of their IoT devices are running it. And the bug reports that come back are great because they've broken Microsoft's compiler. So then you get a compiler team working on a problem and they're coming up with like really esoteric corner case examples where you have like, some random like combination of stuff that then leads to this weird corner case outcome. And they're like going, oh, here you have a bug in your library and it's invoked using this. I'm going, So yeah, they found a bug in Clang. Sorry, they found a bug in outcome when running on Clang, and it ran fine on all the other compilers. I'm like, what are you, Microsoft compiler team, doing investigating Clang? But I'd ask no questions. Something interesting is going on there, and that's probably secret. Either way, I'm really glad that they came up, with bug reports. They've been really, really great, the Microsoft team. They've added so many bug reports with fixes and proposals for fixes. So thanks. So this is the first new vocabulary library in Boost. Some years, I think the last one was optional, but I might be wrong on that. A vocabulary library is one of those things that everybody uses as a fundamental core type that gets used throughout any large code base. We've not had very many new ones in C++ recently, but here's one of them. Yeah, so it took a year. So the first peer review came in, it was failed and rejected. So they said, go away, throw away everything you've done and do it again like this. So I spent a good 6 months putting it together and redoing it exactly like this, brought it back for second peer review. This one was much closer to 50-50. Vocabulary libraries generate lots and lots and lots of bike shedding. Everybody has an opinion. I can't remember how many hundreds of emails that went backwards and forwards for the second peer review. But it was a lot. And I remember all of my life just getting sucked down to doing nothing but reading and writing emails for, I thought 2 weeks, because the peer review normally lasts 2 weeks. And then they were like, oh, well, we haven't decided this yet, so we're just going to have to extend it by another week. And then after that, they had to extend it by another week again. So the total peer review for the second peer review was about a month of just never-ending, really long emails, arguing over very, very minute technical points. And we eventually arrived at a consensus, and that consensus just about pushed it over the line. I then had to go off and do all the changes that came out of that, and I think I came back for a third review, and then it was sort of got through. So that's where we're at. The code, as I say, is done. It's being used by lots of different people. The only reason it's not in Boost yet is down to the documentation. So documentation hasn't been touched since the review. I hate doing documentation. I've rewritten the documentation 6 times now, completely from scratch. And I actually would break an arm before having to do that documentation again. Fuck me, do I hate that stuff. But on the other hand, you only do it once in your life, once in your career, to get a library into Boost. And I have to say, it is a career-defining moment to get in, because it's so very, very, very hard to do, and it takes so much effort. But I have to do the documentation again, and once this contract's finished, I will sit down and I'll do it, and I'll hopefully aim for a Boost release next year, and it'll be out the door. So it's coming. Yeah, it's how many tens of thousands of hours. Anyway, so how it works is it lets you set per namespace rules for localized deterministic error handling. So what you can do is you can say that in my database, in my namespace for my local library here, I'm going to set up that this type here and these are the types will all have these sets of intricate rules of how they will interact with one another for handling deterministic exception. So for example, between this type and this type, it'll be deterministic, but if it goes between this type and this type, I want you to throw it as a standard exception, and this is all fully programmable. You don't actually have to do any of that. There's a set of default rules set up that are probably good for 90% of people. Straight out of the box, you don't have to do any of that stuff. But if you want to reach down into that deep, deep well and do heavy customization, you can. You can also talk about other libraries. So you can have one library over here using one version of outcome, another library over there using a completely different version of outcome, and you can set up rules that will have those two incompatible versions of outcome talk to one another. So all of that just works. And it's kind of handy because it means you can scale out to arbitrary sizes of code bases with arbitrary numbers of third-party libraries, all doing their own custom thing, and it'll all interoperate. And this can be injected from outside. So your third-party library A, B, and C, you as the application writer can bring A, B, and C in, and they all don't know anything about each other at all. And you can inject rules to say that A will talk to B this way, and A will talk to C this other way, all from outside. So that's kind of handy. It really allows a lot of customization. And that is basically what I just said. Yeah, you can completely substitute for C++ exceptions, except these things are deterministic and 300 times faster. Yeah, it doesn't take up much compile time. I have a super duper light version that's so light, it's kind of a pain to use, but it has virtually no impact to compile times. So if you've got a multi-million line code base and you want to include this light outcome into every single header file in your entire code base, you can do that and there's virtually no impact. But you will, it's a bit painful to use because there's very little of convenient stuff in there. But on the other hand, that makes it really, really quick to come in. And you can, of course, turn off your C++ exceptions globally, and this stuff all works. So it works in your games, embedded systems, devices, and so on and so forth. And it looks very like Rust, Swift, Go. Yeah, you're basically the paper I just wrote and published. It's a library implementation of the same. You need C++ 14. C++ 20 is greatly preferred because I use concepts. If you don't have concepts in your compiler, we fall back on a SVN-based emulation, which is much worse. So if you can turn on concepts, that's really a positive move. As a result of having to need all this fancy new stuff, we have quite modern compiler requirements. I'm really sorry about the GCC 6. It does actually work pretty well in GCC 5 most of the time for most people's code bases. If that's any use, just don't use constexpr, because if you do, it's going to die really, really badly. If you want to use constexpr, in fact, don't use GCC because we trigger a number of constexpr evaluation bugs in GCC. GCC maintainers know about them. They kind of go, we can't fix that because it's too hard. So they just keep pushing the version out of when they're going to fix it. But they have a repro, and at some point they'll get it done. I have to again call out to Microsoft here. Back in the day, Microsoft's compiler really, really did not work well. But I have to really hand it to the team over there. They worked with Outcome and with me, and we got that compiler up to the point where it works perfectly in constexpr now. You can do some crazy stuff that even crashes Clang, and it just works flawlessly in Visual Studio. They've come so far in such a short period of time, but that's because they've got a whole lot of really, really great people who are just dedicated on getting this stuff to happen. So thanks, Microsoft, you know. Yeah, and you can configure it to work with error code or status code or your custom type, or anything else you might feel like. There's pre-built bindings for status code and error code, so they're obviously going to be an awful lot easier, but you can do completely your own stuff as well. I'm probably going to just quickly flick through these because I'm pretty tired, and I can see you're all pretty tired, and I'm beginning to just warble incessantly rather than actually talking properly. All I can say is I'm getting quite tired myself. But I'll publish these slides afterwards, so you can run through the code, and if anyone has any questions, do please ask. This is an example of code without outcome. You can see here that we're using error codes directly. I would point out the EC clear. These are really, really easy to forget to do. There was a bug in libc stud C++, which Jonathan Wakely put into it because he forgot to write down EC clear. And that bug triggered something really, really bad, and I can't remember what it was at the time, but I remember Jonathan coming along and going, fucking EC clear, because it's one of those things that you just have to remember to put in, and if you don't, you never know that you didn't do it up until someone finds a security vulnerability or something really horrible. So they're real painful, and if you can get rid of them, that would be great. Here's the calling of the same code. You can see it's kind of a bit messy. You have to kind of extract out the EC and do some testing, and you know, it's fine. If you have outcome though, you can do a bit better. So this is the same function before, but it's much cleaner. So you simply return the error-C invalid argument directly, because there is a constructor that can see that there's an error code error-C that's convertible to an error code being fed to it, and automatically constructs. By the way, the result int up here is the difference. So it'll automatically see that you're giving it an error-C. It will automatically construct an error code from that. Down here, here's where you can put an error, because it has a brace initializer list that lets you construct that direct. And if you can return the FD directly, it sees the fact you're returning an int, and it'll construct from that directly. So it's just quicker, much less boilerplate. You just get straight to it. It's interesting because all of this stuff was rejected for expected, which is the thing that WG21 are standardizing, which is, it used to be much fuller fat, but they've been pruning stuff away. So all of the stuff's been removed that makes it fun and easy to use. So it's now you have to type an awful lot of stuff when using expected. Outcome, you just don't, because it just infers all of this stuff for you. And it makes things much happier. Here's one way of calling it. You can call it in the same way that we were before with error code, this really, you know, spread out method, which has lots of if statements and whatever else. But why bother doing this? Because this takes too long. Let's just do this. So here's the interesting thing. If you have a result being returned by your result open function, and it has a value in it, value will extract it out and put it into the int, and you can just get on and use it. If, on the other hand, it failed, the value accessor, the observer, will throw the error as a system error for you, because the default rules that you've set up have told it to do that. You can override those rules and tell it to do something else. That's totally up to you. But the default rule for this just automatically throws it. So it means that when you're writing out code that uses outcome, you don't have to have if statements. You don't have to have all of this logic testing. You just get on with it and let the default rules work. Question at the back. Sorry, say again? Why not implicit conversion is the question. Because implicit conversion is bad. It would never have got past the Boost peer review if there'd been implicit conversion in that part of. So to explain, input implicit conversions might be allowable sometimes under very restricted circumstances, which is what outcome implements. Implicit conversions out of something are a serious no-no. We did a lot of that back in the day, and we've learned not to do that. I will give you an example of code I was looking at today at Verizon. So my job at Verizon is to take a very, very old code base written during the early 1990s and make it work on C++17. So I'm porting from VC6, actually. It's Visual C++ 6 from about 1996, and taking that all the way up to Visual Studio 2017. The hardest part, by the way, is COM. So Microsoft COM, all of the COM components were built against the 3.1, pre-3.1 COM building model, and I'm having to port all of them to effectively whatever Visual Studio 2017 does. It's so much fun. Anyway, one of the problems that I had today was when I was looking through the volume of output was that there was the string class, very unfortunately, has an implicit converter on it. And if you compare it to a star tchar star, the string should automatically decay to a tchar star so that the comparison can work. But the trouble was that the comparison was getting confused because for some reason or other, nobody had defined the Unicode macro so that tchar was defined to being a char rather than being to a wchar. So this is an example of where implicit conversions can produce really unhelpful error messages. And you have to bear in mind there's thousands and thousands of these error messages. And you're kind of like plowing through them going, oh, I bet it's just that somebody forgot to define Unicode again. And that turned out to be the case. But that's only because I know that now. But earlier before, back when I started the job, I was like going, what? So implicit conversion's bad when they're coming out of things. The only one I would allow for is explicit bool, because I think that's safe enough in C++11. But other than that, implicit conversions out of a thing, you try to avoid it. Unless you're doing evil, like Boost.AFIO. So that's a new library that just entered Boost. It's an expression template library. It's really cool, but it does evil, like implicit conversions to produce temporary objects, which then when you combine them with other things, builds up the expression template syntax. But, you know, anyway, we won't worry about that. There's a lot of very bright people in Boost. Okay, I finish up in Dublin in end of November. I become available in January. So if any of you guys are willing to hire a remote person and you liked what you saw, you can give me 90% remote. I'm very interested in hearing about you. I live in Cork, I don't live here. There's my LinkedIn. There's the link to Outcome. And thank you very much for coming and being bored by me. Question at the front.
Can you switch to the slides, to 2 slides back?
2 slides back. Here we are.
No. Back again.
Back
Yeah,
again.
This one.
This one.
Yeah, so I was implementing a very similar class as well, and
Oh, cool.
I stuck with the problem that the result class, if you return it from function, you want to have it optimized to be returned in optimized way through registers like EAX,
Yes.
EBX. In this case, is it guaranteed?
So the question was that this result int, if it gets returned, is it going to get passed back using registers and not spill onto the stack, is your question. The answer is that on x64, it will always use registers. Yes. If you're on 32-bit, it will not. If you're on ARM, it will always will, because ARM's great and passes lots of stuff by registers. And each of your different architectures will vary. You have a follow-up question?
If you extend your result class to inheritance, you want to add additional memory functions. Will it be still returned through registers? Or then
So you're now saying if you extend the result class with extra items, will it now be returned via registers? Well, if it's not actually down to outcome that does any of this, it's down to the calling convention. So if the thing that you're returning, the type you're returning is trivially copyable, and its size is less than 2 CPU registers, then the Itanium x64 calling convention guarantees that you will use registers to return that. And that's just part of the calling convention. If you're on AR64, you get 8 registers worth of return space. So if your item is trivially copyable and fits into 8 registers, it will just use register storage to come back. If you're on Microsoft's compiler on x64, only 1 register is used for returning back via registers. And if it spills past that, then it goes to stack. So it's only on Itanium with GCC and Clang you get the register transport for the most part.
So if it's going to be result tuple int int.
So if the type was going to be result tuple int int, you would be over the limit because result is stored as a struct underneath the bonnet. So you actually have the error type is kept in afterwards. So that would be too big. Go back to via registers. I've been very careful to preserve trivial copyability. So if your types that you put into it are trivially copyable, result will be trivially copyable. Same way as if it has trivial constructor, copy constructor, move constructor, or destructor, all of that gets propagated through. So whatever types you use, the characteristics of them are perfectly replicated. But it's the subset between the error type and the value type. Whatever the intersection is what you get out.
The trivial, I will show you. I even created a thread with GCC developers. If it's possible to propagate structure memory variables through registers, if they are more than 2 quadruple words.
The point is that can you pass things that are bigger than 2 CPU registers through the calling convention? If you use a different calling convention, then sure. So is there not a calling convention for using registers more on x64? I cannot remember. Something like fast call is what I'm kind of thinking, but I'm just showing my age here when I say fast call. Some people who are older will know what that is, but it's hopefully dead nowadays in modern compilers.
There are many cases when we don't really care. Like we use only internal and they never exposed.
I would say as well, inlining is your friend. So if the compiler can inline, it doesn't really matter whether it can use registers to pass this stuff back or not anyway, because it'll just all get collapsed together and hopefully eliminated. I mean, I have some code which does lots and lots and lots and lots of stuff. There's thousands and thousands of lines of result using code. And if you just happen to feed the correct constant inputs into it, it gets turned into a MOV EAX, 0. one assembly instruction pops out of something like 5,000 lines of code. It just goes gone, optimized out. So modern compilers, if you can tickle them the right way, can just eliminate huge quantities of code for you by inlining nowadays. Just don't put it in the main function, because GCC has weird inline heuristics for any function called main, just cause. If it's not called main, it has different inlining heuristics. I have learned the hard way, which makes no sense at all. So when you're in Godbolt and you're testing stuff out, do not call the function main, is what I've learned with just GCC.
And as a summary, with the new proposed style of exceptions, we get non-propagation and this try-catch, which is massive in my eyes.
So you're asking about the non-propagating, non-auto-propagating try-catch syntax, yeah?
Are we moving in that direction?
Are we moving in that direction? Almost certainly not for those who don't want it. So some people really want that, and if they do, they'll be able to opt into it, and then they can do it, and the compiler will enforce it. And then in your company, if you really hate all your coworkers, for example, and they're all people like you, you'll simply say, you'll put a commit check in on your CI service that will simply refuse any code that's not written out this way, and you'll send, just refuse, commit, and reject, and automatically roll it back and push an email out to the person in question saying, please fix your thingy to use fails at all possible times. So that's antisocial, you say. Well, is that not benevolent dictatorship, depending on how you look at it? I have to say, I have worked in clients before where we had some trouble with discipline amongst the team when they were committing stuff, specifically to do with the style guide. So I was told by my management to enforce the style guide. So we came up with a thing where we ran Clang format on the code, and if there was a single difference between the Clang format post and whatever was submitted, you just kick that commit right back to the person who sent it in. And to say that produced a lot of very unhappy developers who had maybe a stray space, not quite the right location. People got really angry about it. But hey, I'm a contractor, so I just do what I'm told. I don't get involved in the politics.
Wait, then we get so many options, like we can use alt style exceptions, new style exceptions, many new keywords, throws.
So you're pointing out that there's lots of different ways of doing error handling. You are correct. There's at least 4 ways already in C++. We're going to add, if this goes through, we're going to take that up to about 8. What I would like to say is that at the minute, the different ways of doing about it, they're all kind of haphazard and not connected. After this, they will now be much more unified to a common strand. So think of it like a tree with many branches. And they all have the same root that comes down to it at the end, which is basically control flow. That's the way I would propose it, but I completely agree with you that C++ is suffering from modifier hell. So if you look at functions, you can now declare something as being overrided or finaled or no accepted or throws or going out to infinity, right? And the thing is, you should see the standard committee papers. There's a whole load more modifiers coming, like lots more. I mean, there's going to be like multiple forms of const expr coming, right? So you can have one type of const expr, but you'll also be able to have extra const expr. That's coming too. So that's a const expr with an exclamation mark after it to say that I really want const expr here. Not just normal const expr, but really const expr. And you'll be able to mark up all of this stuff on your function. So if you look at your function, it'll have like, about 20 different modifiers hanging off the end of it, and another 4 or 5 at the beginning. And this is the C++ we are expected to write into the future. And I think I can safely say that everybody in this room will agree that that's just daft. Something needs to be done to prevent modifier explosion. What to do is hard, though. At the back.
It's becoming really, really complicated. This time I know it was C++ 99, it's complicated. Standard.
So the question is the committee worried about how complicated C++ has become? The answer is yes. In fact, the direction group has had on the private mailing list for just the direction group, which I'm a member of, even though I don't think they realize I'm on it. because I'm not part of direction. But somehow I've been joined to the list, so I get the email and I just say nothing, never ever say anything. But it's interesting to watch the debates going on there. So there has been a running debate now between Bjarni and I can't forget his name. He's a very nice guy, and I just can't remember his name. Anyway, it's very late. And he's been arguing very forcefully for how complicated C++ is for the average C++ programmer, and the steep, very steep learning curve there is coming off of that. And especially that now that C++ is not really a general applications programming language anymore, it's now very much a niche programming language. So, I mean, why would you choose C++ nowadays? You care a huge amount about performance, about determinism. It's like high frequency trading, that kind of application, games, that type of application, embedded systems, that kind of application. Self-driving cars, almost all of them are written in C++ because you need the performance in there for a certain battery consumption power, and the combinations all come out with C++. So these are very niche applications that require very specialist skills. There's also comparatively very few jobs in them, and moreover, those jobs are very much located in tech clusters around the world. And if you're not in that tech cluster, you don't get a job. So I'm sure all of us here in Dublin have noticed that Dublin is not in the top 20 probably of those places globally for C++, the places that pay really, really well. I mean, I know a number of people on the Command Standards Committee who are not far off $1 million a year now in base salary for just writing C++ all day long, and that's because they're in one of those big tech clusters. And they're doing a very specialist programming role in C++, and as a result, they get very, very large sums of money. I don't think anyone in Dublin's on that kind of pay. Not that I'm aware of. If you all are, reach out to me by email, and I'd love to hear from you. So, I won't tell anybody that you're paying that kind of cash. But no, the trouble is you've got that balance. So sure, the general programming language is on one side. I think that's kind of dying away now. And what you're getting is this very niche specialist type of C++, and we're making it even more closer to the bare metal, bringing it even closer to, again, some of you might know I'm the guy who's writing out the technical specification for the low-level file I/O library, and that will reduce I/O down to the absolute barest metal ends of things. Bryce and a number of other people are trying to get the graphics layer down. So you've got the CUDA compute that's going to get dragged down to the bottom of the C++ layer as well, and that's all going to be put into the standard. So the answer is that yes, we're all aware of it, but in terms of what's being done that's actually achieving anything, I don't think that anything is actually happening. It's just becoming ever more complicated, and everyone agrees it's bad, but nobody's doing anything about it. That's the God's honest truth. You have another question?
That's very nice. So there is no motion to actually see some of the practice made so far, and forget about this, but and for the better way. So we're making figuring out this exception and having is the way it should be. So maybe slowly.
So the question is the ability to unwind past bad mistakes. I think that's extremely unlikely to happen anytime soon because C++ is basically run by the big multinational corporations. So if you look at all the big funding, it comes from them. ISO works via big multinational corporations because they can put people in each of the individual countries, and that way they control the plenary votes to ensure that votes go the way that they want to have it. And big multinational corporations have an enormous incentive to make sure that C++ remains backwards compatible in perpetuity. The fact that I can take a code base written in C++, written around about 92, 94, and port that to Visual Studio 2017 in full enforcement C++ 17 shows how much backward compatibility there is in there. I mean, I'm kind of lucky because that code is pre-STL. So because there was no STL when they wrote it, they had to invent all of their own local template library. And as a result, that just gets forward ported into the C++ 17, and it just works-ish. So that's an example of where big multinational corporations really like that part, and undoing it, I think, is virtually impossible. I'll put it another way. Digraphs in C++. So digraphs are a way of indicating characters by combining other characters that have nothing to do with them whatsoever together. So if you write some random whatever, you can get the compiler will see a different character from what's actually there. So the preprocessor will expand them out differently. So they finally killed those off. Was it trigraphs rather, which are even worse. And they did it despite the fact that IBM did every single thing in its power to stop it. And IBM went all the way to going out to plenary vote and reaching out to the different countries to have them vote against this thing for killing this feature that nobody except IBM uses. And the reason why IBM wanted it not killed is because IBM uses it. So they have a whole lot of code that's using it, and they want to keep it in. But like people were like, well, you can just keep your compiler, which is IBM's compiler, doing that into the future, and all the rest of us can just ditch these horrible things for what they are, because they're just an abomination, and they get into so many trouble, and they cause so much trouble for different people. So just kill them. And IBM still fought it to every single extent of the worth. And I'll tell you the reason why I think, and I don't know, I might get in trouble if this goes out too much again on video, but I think IBM would have won that battle had it not been for the case that they've cut back their headcount so heavily in recent years that I think that they had lost the respect of the technical and engineering community, because they'd killed all the top people that they had. All of them have left. They've fired so many of their top people in recent years and replaced them with young people. And those people don't have the kind of clout in terms of political clout with the rest of the leadership around the world. And I think when they were coming along and they were saying, you can't do this at any cost whatsoever, people were like, well, we don't really respect you as an engineering organization anymore, IBM, so tough, But had it been a few years ago, I have a feeling that they actually would have won, because IBM had such cachet in the community. They've been there for such a long time, and they've got this big, engineering prowess. So I think they probably would have won a few years ago, So, backward compatibility is both the greatest thing about C++ and also the terrible thing. It gives people like me jobs, and probably a fair few of you looking after legacy code bases in perpetuity. And that's great, because, in Ireland, we don't have a huge deep pool of this kind of stuff. But equally, it's very very restraining sometimes, because you are locked into only ever using features that were in C++ back in 1995, for example. So not even any exceptions, none of RTTI, none of even any of that new stuff. You're like in 1995 forever. And the trouble is you can still configure modern compilers to pretend to be in 1995 in perpetuity, and that still works. So it's a plus and a negative. I don't think anything will happen about that anytime in the near future. I have a horrible feeling that Rust will actually have to come along and threaten C++ a whole lot more before anything really changes in that area. Now, that said, again, I probably haven't had too much of that I can say this. There is an undercurrent of some people who have been talking about a language which is a reboot of C++. So this language would be completely incompatible with C++, in terms of the syntax would be completely different, but it would be source compatible with C++. So you could have existing C++ mixed with this new C++ in the same source file, and it would all link and work and call into one another, but the new syntax would look nothing whatsoever like C++. I have seen some examples of the proposed syntax. It looks a little bit like Python, but that's about my best description of it. I actually would say it's not quite Python. It kind of looks... have you ever seen NIM as a programming language? NIM is a kind of statically compiled Python. It looks more like NIM. So that's what the kind of stuff they had floating around. And people were arguing about the merits of, whether, because they wanted to make it look so obviously not C++, because they want to preserve copy and pasteability, right? So one of the key things you always see with C++ is it's always possible to copy from one place and paste into another, and the code will always work. So that's why we never have namespace modifiers. We never have anything to change things to the global state. You always have this per function stuff, so you preserve copyability, copy and pasteability. And the key part of this new language is it would look so unlike C++ and yet be source compatible with it that you wouldn't have no way of getting confused. I mean, even the for loop looked nothing like a normal for loop, right? It was completely different. And the great advantage of this new C++ reboot is that you can still compile all your C code as C++ because it works in old C++ mode. So you can still copy and paste all your C code and that all works, but you can break into new C++ at any time you want to, in any particular function, any particular namespace. Obviously, it's a huge shock, but yes?
What happens with Rust? I haven't heard about Rust.
Oh, you're asking me about Rust. Yeah, so a few contracts ago, I ended up having to write Rust for that contract. Now, I signed on that contract to write C++, but about a month into it, they went, oh yeah, you're going to be writing Rust from now on. And I said, well, I don't know anything about Rust. They said, that's fine, just get to it. So, so I had to learn Rust really, really quickly. And I spent my time mostly beating my head out against the borrow checker. And also ran into lots and lots of problems with standard library. Now you have to bear in mind, I was on Rust 0.8. So this is a long, long time ago. This is many years ago. And things have greatly improved since then. I would also say the compiler used to be very slow. It had terrible context evaluation abilities, but all of that's been fixed and improved as well. Cargo had a lot of problems back in those days, which is the build manager. That's also been improved in a big way. Let's see. I know some of the Rust leadership quite well at this stage, after these years have gone by. They're all very reasonable people, except for those of them who are not, because some of them are really zealoty, and you're like, but you get that with every language, including C++. I think Rust is the best thing that's happened to C++, mainly because it's forced C++ to start evolving. Ever since Rust came along and became a big threat, the committee has gone through, processed, I think it's about 20% more papers per meeting than it did before. So that's an example. That's a conscious decision by the committee that they were feeling they're getting lapped by Rust. So they decided to up their work rate. And that's why the evolution of C++ has sped up. I don't think it has been for the better in terms of quality. I don't know if you guys have looked very much at std variant, but I think std variant is a classic example of what happens when you rush a feature into a language before it's ready. There's a lot of problems with std variant. Probably a better person who will get in trouble instead of me for going into detail would be, see, this shows how tired I am. David, my friend David, who works at Bloomberg. He's actually on the Boost steering committee. He has written blog posts about the problems with std variant. I know Anthony Williams, who's over in Britain. He did the threading library in C++. He's written about problems with std variant. I think everybody can see the problems with std variant, and they were not unobvious when it went into the standard. And a number of people said this should not go into the standard because of these problems, and they were ignored because C++ 17 was lacking in big killer features, and it was felt that it had to have big killer features to advertise it as being a big thing. And I think that was very unfortunate. I think we should not ship before it's fully baked. So that's some of the negative stuff that's come out of this rush to keep up with Rust. But there's also some good things. I think modules would not be happening at all if it weren't for the pressure that's coming off Rust. I mean, Java finally shipped modules, right? Just there a year or two ago, after like a decade and a bit of finally getting them done, but they finally shipped modules. And C++ has been working on modules now since about 2003, and we might have them by 2023 at the current rate, maybe. So 20 years is not too bad going. And I mean, they're hard, they're really hard. And if you're in the committee meetings when they're being discussed, they are really, really in-depth reasons why there are problems. I mean, you've got John Lakos standing up and saying why he can't deploy modules at Bloomberg. And he has a lot of very, very good reasons that all the modules proposals are fundamentally flawed and none of them will work. And you're kind of going, well, if John's saying that, and he has these really good reasons that I totally buy into, what are we doing? Should we actually ship these things? And then everyone's going, nope, we need modules for C++ 20/23. It must happen. And I worry. I do worry. I think shipping before they're ready. I should probably say as well, just so that it doesn't sound I'm being too biased, I have an alternative modules proposal. My alternative modules proposal is to not do modules, right? I don't think they can be done, personally. I think we should standardize Microsoft COM. Now, I have an opinion of one on the committee on that. Nobody agrees with me on the entire committee that there's any sense in doing that whatsoever. But my argument is going to be this, and it's very simple. We know COM works. It's horrible, 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 but we know it works. It is a standard proven technology that we know it works. And we know how bad it is, and a known terrible thing is much better to standardize than an unknown, maybe a good thing. And that's my issue. Modules is full of, it looks like it could be good, but there's lots of stuff in it that might go horribly wrong. I would much prefer to standardize something that everybody hates, but knows really and understands really well, because we know it works, and COM really does work. I obviously would pretty it up, don't get me wrong. I would, add and remove a lot of stuff to it, but it would essentially be the same thing. And in fact, it probably even be compatible with existing COM. So you'd be able to write shim layers that would automatically call between them. And that's my solution to modules. I think that's a much better way of doing it. You may be able to find a very lengthy paper by me kicking around on the internet about that I wrote years and years and years ago. My argument is still that that's the best way forwards. I think that the committee and all the compiler vendors will spend an enormous amount of time on modules, and they could just not do that. Just don't do it. Do something else. Use that time that you're going to invest in modules and do something more productive that you'll get more results quicker, lower hanging fruit. But that's my personal opinion. And as I say, I literally am an opinion of one. When I said that to Herb Sutter, I remember he was eating his breakfast at the time, and he actually started laughing and coughing so hard. He spat out his breakfast, and he was like trying very hard to, not go red in the face. And I was worried I, caused him to choke to death or something, So, but he thought it was just hilarious that anyone would even think that, let alone propose it as being actually something realistic. So Anyway, I'll win one day. We'll wait and see. If modules really tanks, I'm actually going to put a paper up to say, Microsoft COM, solution and cause of all the problems in the world. So we'll see what happens. I'd say one more question, and then I think we'll have to go, yeah, because, yep.
Really quick question. I just want to know if using those outcomes, can I return a payload when throwing exception?
So you want to know, can you throw a payload when you return an exception? Yes, you can. You can customize the payloads absolutely in all the different ways you want to do, and you have multiple ways of doing it because it's Boost. There you go. I must run to my train, I'm afraid. So thank you very much, everybody, and I'm sorry for cutting you all off.